Well, good morning from a sunny and crisp Toronto, Canada. Welcome to today's webinar. My name is Armin Mulkey, and I will be your host and moderator for today's live event. Today, our Director of R&D, Mr. Peter Martin, will be talking about our approach to mechatronics, in particular, our extensive experience designing and developing innovative mechatronic systems for the academic market, which has pioneered a new approach to mechatronics education. And just a bit of a background on Pete, he is an experienced engineering educator who's been a member of the Quanser R&D team for over a decade. As Director of R&D, Pete is responsible for the vision, strategy, and management of all our R&D activities, ranging from core educational and research products to software applications, curriculum, and mobile apps. Pete, the audience is all yours.
Thanks, Armin. And thanks everyone for coming. I'll just turn on my camera for a minute so you can all see me while we get started here, and then I'll turn that off in a minute or two just to save on bandwidth. There we go. Beautiful. Okay. So what we're going to talk about today is essentially our take on mechatronics, specifically what we're calling modern mechatronics. We'll start by talking a little bit about just some simple questions that it turns out may or may not be quite so simple in terms of what is mechatronics? How do you even define that field of mechatronics? And then what is important to mechatronics from an engineering education perspective, from an industrial perspective? How do we deliver the skills and experiences that engineers need to be able to succeed in the fields of modern mechatronics design and development? And then we'll look a little bit very briefly at the adjacencies to mechatronics. It's another very good question that we've been trying to grapple with for the last few months and years in terms of how does mechatronics overlap emerging areas like machine learning and robotics and other fields that ostensibly seem like they have the same elements. And then finally, I'll show some examples of how you can deliver these experiences to students, and also how we're trying our best to create solutions around this ethos of modern mechatronics and the take that we have on what that means, which without further ado, we'll get into. So as I said, let's just start with a very simple question of what is mechatronics? This should be a relatively simple question. I have a degree that says that I know about mechatronics. Many people now do, many students especially increasingly have mechatronics degrees. But that being said, the definition, the real all-encompassing statement of what mechatronics is still remains somewhat unknown, somewhat vague. When we started down this path of developing products for mechatronics, we did that very question. We asked that very question, and we did a lot of research to try to decide what that meant to our customers, our markets, how we could really create the be all and end all of mechatronic solutions. And as I'll talk about a little bit later, we're still doing that work today because it is a little bit ambiguous. There are lots of specializations, lots of approaches to how to deliver a mechatronics course, from design to an application-centric course to specializing in manufacturing. These types of activities you see are here on the slide. Building robots, doing line following, doing investigations into how components and systems come together and how you build them up into complex systems. This is absolutely encompassing mechatronics, but the approaches, the key elements of mechatronics are still somewhat vague. So to a company like ours that creates solutions for mechatronics, that might seem like a problem. How are we going to address this? How are we going to make a solution for mechatronics if it's a little bit indeterminate what that is and what that best solution looks like? But to us, it was something of an advantage, because if we look at what does mechatronics mean to students, we can talk to a lot of students, a lot of graduates who work for us, who went through mechatronics programs, but what it means to them, what they learned about, what they view coming out of these programs as the essential learning objectives and skills for mechatronics. We can talk to employers, we can talk to ourselves. We are a mechatronics company. We are one of those industrial employers for mechatronics engineers. And so we started there. We looked at what does mechatronics mean to Quanser as mechatronics professionals, as a company that's been designing and developing complex mechatronic systems specifically for academia, but also for industry and for research for over 30 years. What do we view as being the core elements of this modern mechatronics category? And really what we view are being all these systems you see are all the systems you see around you nowadays, these increasingly complex and integrated electromechanical systems that are interdisciplinary by nature, interconnected, and interesting. They're fascinating systems to work with. They're the ones that you see in the news and on YouTube as being the really exciting things to watch. Boston Dynamics, SpaceX, Tesla, all these companies, they're building mechatronic systems. And so for students, there's a lot of motivation that comes out of that. And there's a lot of elements that they want to know about. They want to investigate and learn how they work. And again, that's an advantage for a company like ours and for institutions who specialize in mechatronics, because that motivational element is an absolute catalyst and absolute key to student success. And so what we did was take those notions of what mechatronics is as a field, as an application of engineering, and from there, we derived these four key elements of what we view as being the essential outcomes, the essential objectives of engineering education when it's applied to mechatronics. So starting with this prioritization of design intuition over design experience, what we're getting at there is really with these complex systems, this diversity of applications of all of these specializations in mechatronics, design intuition is increasingly becoming far more important than direct experience. So when you're designing a product, an electromechanical system, to us, that process is a series of decisions, a series of educated choices that you make as a design engineer. And because mechatronic systems are, as I said, everywhere, all around us, everything from snowplows to airplanes, it's really difficult to give specific direct experience to students. It's far more useful and far more valuable for them to know, generally speaking, what best practices are, how to make informed decisions if they've never been in that position before or had to make that position in the past. And that builds on literacy over specialization. Again, because mechatronics is highly interdisciplinary and it's highly generalized and multifaceted. Having literacy in engineering generally, understanding what systems engineers do, what electrical engineers do, what mechanical engineers do, even if you're not one of those things, is extremely important for a mechatronics team, because that means that you can see where they overlap. You can see the considerations, the design decisions that are going to influence other parts of that design and ensure that your decisions, your part of that design doesn't conflict, doesn't cause issues. Exploration over creation, again, complexity, highly integrated systems, they really need to be explored, to be dissected and understood, as opposed to having students try to build them up from the component level. Increasingly, if you want to have that authenticity, which is the last point you'll see here, that experience that students can really relate to the real world, they can't build that. They can't build an automation line for factories. They can't build a self-driving car from scratch necessarily in the time constraints and effort constraints that modern universities have, but you can dissect them. You can understand the components, understand how they're built. And that's a very exciting and a very valuable experience in and of itself. And then finally, authenticity over abstraction. We really talk a lot about authenticity, about giving students motivational experiences, experiences that challenge them, that give them insight into how these skills are applied in an authentic way, in a way that means that they understand the real downstream applications. They understand where this will be used again in the future. And then we don't abstract away that complexity. We embrace it and show that this is the skill set, this is the application that you'll see later on in life, whether it's in industry or it's in research and academic pursuits. Just to touch in a little bit more detail on those, just to make sure that we're all on the same page. Design intuition, as I said, what we view design is, from an electromechanical perspective, is a series of decisions where you're choosing components, algorithms, integration options. You're making decisions at every point. And as I said, building intuition that really gives students the right skills and experiences to be able to make those decisions regardless of what they're building and how it's being built and what the team is they're working for. It's absolutely essential, because it means that in that diverse and varied mechatronics engineering category that is all over the industrial and academic space, they'll have a better idea of what the right move is when they're making those design decisions. Engineering literacy also, as I said, builds on that with interdisciplinary teams from mechanical, electrical, software applications. These are the categories that we have at Quanser. These are the functional groups inside our R&D department. And that's for a reason. As I said, we are a mechatronics company. That's how we make sure that we can build the complex systems that we build. We have specialists and we have generalists in other categories. And there's a nice healthy flow back and forth where if you're a specialist in application design or in mechanical design, it doesn't mean that you lose that specialization, you lose that expertise, but because of the interdisciplinary nature of our projects and our project management, you get that exposure with all the other disciplines to the point where you understand what they're concerned about, you understand what they do, and therefore you can talk intelligently about the considerations that need to get looked at, and you can talk intelligently about how the decisions you make influence those other categories, those other elements of a complex mechatronic design. And finally, this idea of design dissection. How do you take these complex systems you see here, an automation line building parts of a vehicle, and give students those experiences, those skills, not necessarily building up something like that from the ground up. You see behind there the sort of classic approach that might have been taken in the past where students would breadboard and use microcontrollers and things like that and 3D printing to get an experience that might ostensibly be viewed as a design experience for a mechatronic system. Depending on the outcomes, we really view the dissection of a complex system as being far more valuable because you don't lose that excitement and complexity, and you don't lose the real applicable skills, as opposed to having to have students struggle through the component level design ground up development cycle. And finally, this idea of authenticity, which really, as I said, overlaps that previous topic. It's mechatronics is really centered on design and development of electromechanical systems. It's inherently practical, but at the same time, it needs that appropriate level of theoretical rigor. It needs to have generalization so that, again, students have intuition. And then finally, authenticity builds on that motivation you get from the excitement from the exploration of these complex systems to really get students the context and the motivation to follow through on these investigations. That being said, that authenticity doesn't have to be these fantastic categories that I talked about. It doesn't have to be SpaceX rockets and autonomous cars and self-driving drones and all sorts of exciting things. It can be as simple as I said, snowplows or doorbells or systems that may at face value not seem as exciting, but if there's an authenticity, a motivation inherent in the challenge, they can be just as exciting for students, if not more so. When we were doing design courses at one of the universities that I worked at, we would often give students challenges that were completely outside of what they would typically be exposed to. Things like doing environmental monitoring of waterways around the area where the university was located, working with interdisciplinary teams from environmental engineering or other disciplines to see what challenges they faced and how mechatronics engineers could solve them, working on prosthetics for children or for adults to be able to ride bicycles or drive cars, like all sorts of, again, authentic challenges. They're not as necessarily fascinating or exciting to engineers as backflipping humanoids, but they have that level of authenticity and engagement that really ensures that students are going to want to succeed and see how in the future they can take on similar challenges. And then finally, there's this concept of projects versus products. I've talked in other webinars about that concept of how you give students a glimpse into what it means to create a product, not just create a project, not just something that's been made once for a single use case to maybe work for a single day in your evaluation, and then kind of sit on a shelf in a TA's office or in your bedroom for the rest of your career. When we really work as mechatronics engineers in an industry, especially, these systems we develop are meant to be made hundreds, if not thousands of times and last for years. And that's a completely different challenge. And obviously you can't give students that challenge, but you can absolutely give them insight into what would change, what would be a critical decision point if they were to go down that path. And again, this introduces lots of opportunities, case studies, industrial collaboration, guest lectures, all sorts of other opportunities to, again, give them that authenticity of what happens once they leave their undergraduate studies. But how do you do that? How do you dissect a complex mechatronic system into an authentic experience to build the intuition and literacy? How do you pull all that together? So for us, that really starts with the component level. You start at the bottom. Our systems are built up using actuators, communication systems, sensors, processors, all those building blocks of a mechatronic system. And then on top of those, once students have familiarity, they have a functional understanding of what those components are and how they work and what they give the rest of the system in terms of information and how you work with them and interface to them. We build on top of that systems, devices, and algorithms. So algorithms to take advantage of those components, things like signal conditioning or kinematics, devices that are built up from those components to be able to have, for instance, actuators and sensors come together into a mobile robot, or to have communication systems sit on top of processors. And then overarching systems where you have multiple devices all working in tandem to a common goal, especially with the advent of edge computing and IoT. These interconnected systems are also really becoming essentially mechatronic systems even in and of themselves. They have, it's very difficult nowadays to separate out some of these lower level devices into individual devices because they require a connection to other systems. But really that is mechatronics. That is that core of the elements that go into a dissection, that go into an investigation of this complex systems, and how we generally, when we build curriculum, categorize those experiences so that students can scaffold their skills to the point where they're ready for the application, they're ready for these mechatronic systems to do something. You can see here some examples of outcomes that we've worked towards, things for component literacy, like an understanding of diagnostics, an understanding of integration techniques, control systems, even like, as I said, things like design for manufacture, costing, regulatory requirements, component selection, reading data sheets, all those real low level essential tools and techniques for component integration and for mechatronics generally. And then once you build up from there, you can get into things like device proficiency, how you apply algorithms to systems, how you work with different degrees of freedom, different types of embedded computers and communication paradigms to be able to make those components into functional devices. It doesn't end there though. As I hinted at, you still have this application layer that needs to sit on top where you take those and they do something. And to me, that's really where we get into those adjacencies of things like robotics and automation and intelligent systems. They're the application layer that sits on top of mechatronics. To me, if you look at mechatronics as the foundation, you the act of designing and developing and integrating components and algorithms and devices into mechatronic systems, that is the essence of mechatronics. That is the core of what a mechatronics engineer does. And then autonomous systems, robotics, those disciplines, they're the application of that system. So it's like there are some examples here, things like robotics is sciences to engineering, or for autonomous systems, it's not the design of the robot or the construction of operation, but the behavior that autonomy is responsible for. The rest is the responsibility of mechatronics engineers. So it's almost a general a generalized field where you take your cross-disciplinary skills, build up electromechanical or complex integrated systems, and then the layered intelligence, the layered application context, what you do with that system outside of perhaps in some corner cases where there's a very specific use case that is not going to change, something like a dishwasher or um, a more simplistic system. That is the goal, is to build up something that can then have that layered intelligence, layered autonomy put on top of it. And I mean, that's, so if you look at how you can complement these thoughts when you're delivering a mechatronics course, I'd really encourage a lot of educators to look at how mechatronics, again, it does to a certain extent end with the system and with the creation of that electromechanical platform. But to be able to design something to be effective for robotics, for autonomy, for information systems, there needs to be some understanding of how it's going to be used, how it's going to be applied to those challenges. And so having at least, again, that engineering literacy for those adjacent topics is also crucial. And now looking at what Quanser has been doing to be able to address these things as a company, we really start with looking at our mechatronic systems, our platforms that we develop. We make sure they're highly instrumented, they're electromechanically flexible, open and customizable. This ensures that, again, no matter what that application is, all those different diverse fields from IoT to intelligent systems and robotics, they'll be able to fit the bill. They'll be able to be that foundation that you can build those applications on top of. They're reliable and repeatable and robust. Those are general goals for most mechatronic systems. You'd like them to last as long as possible and to work reliably and repeatably. Again, documentation is also key to being able to serve as that foundation so that you don't necessarily have to worry about interfacing or customization or how you work the system, how you drive it, how you operate it, but more what you do with it should be the focus. And then finally, obviously, we support and maintain our systems again as an overarching goal. And that diversity is there, as you can see, with the collection of platforms that we develop. And looking at this, it kind of begs the question again, how do you dissect these? How do you deliver those four pillars of what we view as being modern mechatronics using one of these systems? So let's take a look at that. I think we'll focus in on this Qbot. It's a really nice platform to show some of these fundamental concepts of mechatronics. I'm going to be using, for this particular case, a virtual Qbot, just because in my bedroom, while we're still working from home as a company, it's challenging for me to be able to give a really effective mechatronics demonstration. So that's, again, enter the advantage of digital twinning and our virtual platform. So I'll choose the Qbot 2 here. You can see here now we have a space, a virtual space, where I can play with the Qbot. And what I'm going to do is just open up MATLAB. And in MATLAB, you can see here we have even our courseware for mobile robotics that's applied to the Qbot broken down into some of these similar categories: computer vision, kinematics, mapping and localization. These are the applications of that mechatronic system. But if I go into introduction, you can see that we're dropping down a level. We're dropping down to that base component, that base movement, and how things like kinematics apply to an actuator. So if I open up just a very simplistic example of how you can show the interface between actuation of this base platform and, again, how an algorithm can be applied to that to build it up into a device that moves around, I'll just quickly run this Simulink diagram. What this is going to do is connect to the virtual Qbot. You can see here now I have my camera feeds loading up so that I can see what the camera is seeing on the Qbot. And you can see here the interfacing is very simple. I'm taking keyboard inputs from my keyboard here at my computer, turning those into commands going to the two separate motors, pulling encoder information from those servos, and applying a kinematic loop to that, as well as obviously the camera feeds as well, so I can see where I'm going. And so you can see here I have my virtual RGB and depth information. It matches what I have in the virtual environment as what the robot is seeing. And if I start driving around, let me just move this over a little bit while I drive around. You can see here that the keyboard commands that I'm sending are going to move those actuators. And just from this very simple experience, as a student, you can start to get a feel for what the kinematics means for this robot, what actuating those two motors and those two elements means for the sensor information you're getting, and also for the actual movement of the device. And to build on that, if I just stop that particular model and I'll just layer on top of that another level of intelligence, now what we're going to be looking at is how can we take that camera information and try to automate that process of moving around the space, in this case, following the line. So you can see here I have now a threshold that I'm applying to my RGB information to pull out this red color. And then I'm going to use that to build a blob or an area that I want to identify as being the largest section of red that the camera is seeing, and then finally drive the robot towards that. So if I run this code on my virtual robot, very quickly we should see that it will identify that line as being its target, its orientation that it wants to aim towards, and then move towards that. Hopefully, oh, I lost my threshold. Just give me 1 second here to try to get that threshold back. So basically, again, despite the complications that students can encounter, I think I need to aim a camera down, for instance. That would probably be a good move. There we go. Now it's working. So again, the challenges of a physical system, the challenges of this integration where everything was working, my algorithm was seemingly functional, it was seemingly following, but at the same time, I hadn't pointed my camera at the target. It was missing the element of this space that it was scanning to be able to know what to follow. After I moved that camera down to a better orientation, bringing in that mechanical aspect to the vision aspect to the integration levels, now my algorithm is working. You can see here with the blue dot identifying that point that it's going to aim towards. So whether it's virtual, whether it's physical, whether it's a robot or any of our other systems, we try to give that scaffolded approach, try to give that experience where students can see how the algorithms they develop, the components that have been put together, what their function is, what their element to that system is, and how working with those different parts influences the rest of that overarching mechatronic system. And then we take those devices now increasingly and we try to bring them together into studios to elevate those outcomes, elevate what can be done with those systems. This is just a brief description of how we view studios as being an ideal way to deliver these mechatronics experiences. They focus on problem and project-based work, and the whole idea behind a studio, this is something that's been talked about for decades in engineering education, is to really deliver to students the skills they need to be able to build a portfolio to then be successful in their later endeavors, whether again it's an academic or an industry. They need to have a portfolio of experiences of, again, intuition that they can build on, and a studio is a perfect way to give them that with these open-ended challenges that they can follow up on and try to use in order to build those skills. And I mean, obviously, just from that description, the efficacy is clear. Students get the skills more effectively, they're more driven, more self-directed, which again, in those interdisciplinary fields where there is sometimes only one specialist is also key. And out of it, they get that portfolio of experiences, of applications they've done that hiring teams look for. We're in the middle of hiring at the moment for some R&D positions, and absolutely candidates who have a portfolio, who have a library online or on GitHub or wherever else of projects they've developed, times when they've pulled together mechatronic experiences that they can show us, they absolutely come out ahead when we're trying to decide if they have the right skill set for our company. And those students, again, but those scaffolded divisions, that buildup of these skills, it's absolutely also built into the studio. You can do component exploration across different systems. You can understand all of those outcomes that I described earlier and how they apply to the different systems separately. And then how, when you get to the system integration and algorithm level, you can bring those together and actually see things like basic intelligence or integration of multi-system um, scenarios to really understand how all of these elements come together as with more and more complexity. And then finally, we also have some custom applications we've built up over the years. One example being the pivot project we partnered with McMaster on, where their goal was to redesign their first year experience to try to give students these skills and experiences very, very early on. And using these approaches of combining virtual representations, obviously because of the pandemic, but now in a hybrid configuration this year, giving students those intuitive experiences, those elements of mechatronics design very early on, has paid dividends not just in the student skills, but also in their retention, their potential to continue in engineering and understand how what the benefits are going to be of an engineering career. And so with that engagement, with that motivation, authenticity, all those elements I talked about, we really see it pay dividends not just for the students, but also for the institution. And I mean, finally, this is kind of the overarching culmination of what we view as being mechatronics generally. It's that mechatronic systems, again, they're increasingly complex, they're increasingly integrated. All of those elements I talked about at the beginning of what modern mechatronics is. And those complex problems, not just of creating these systems, but applying them to challenges, it requires complex solutions. It can't be something that students create themselves under the environmental restrictions of a university. And so having these systems to start with that are interconnected, that are interdisciplinary, that can be dissected into these components and then used to scaffold up new experiences for students. It's absolutely something that students are going to need, that system level thinking, and something that's increasingly common as a skill set that's essential to both research and industry. And finally, we hopefully can help if you're interested in this kind of approach, if you want to develop a system or a course to deliver these experiences. We're working on new and exciting solutions day in and day out to be able to deliver these skills more effectively. And hopefully you'll stick with us to see what comes out of those efforts. Thank you very much. Any questions?
Awesome. Thanks, Pete. That was great. Yes, a couple of questions have come in. I'll go through them one by one. First question, excuse me. Given that mechatronics is a hands-on field, what role do you think digital twinning will play in the future of mechatronics education?
That's an excellent question. The way that we're envisioning using it for some of the solutions that we're developing right now is that we really see it as being a way for students to be able to iterate effectively and quickly to get that initial intuition, that especially that initial component level understanding before they validate and gain those experiences in the actual challenges they're facing. So to be more straightforward, basically, if you give them a digital twin of a mobile robot with the ability to see how that robot would behave in a space with a LiDAR versus an RGBD camera versus sonar versus any other sensor that would give them kind of the same information that they would need for their algorithm, but for them to see how it's going to behave in a virtual world, that's a big step ahead, a big step forward without them having to integrate and test those systems separately. And then once they have a general intuition towards what they think will be the most solution, they can try it in the real world. They can validate it. They can get that experience in reality. And that applies to algorithm development. That applies to a lot of the other elements that we were showing here in terms of the initial development and testing and conceptual stage where students don't know what the solution is, but they want to try a few different things. That's something that can be delivered virtually. And then once they have an idea of what they want to do, they can try it in the real world and then validate it. And if not, go back to that initial testing stage.
Great, thank you. So if anybody who's joining us live today has any questions, please keep them coming through the questions pane. Next question. Well, this audience member wants to know if Quanser is currently working on any new mechatronics products.
Yes, I can definitely say yes. A big focus for our entire R&D team next year is going to be on Mechatronics Solutions. We have a few ideas in mind for what we want to do as a company, and the reason I talked about those studio experiences is because that is, I think, another key thing that we've seen be successful in the delivery of these types of courses. And so we're trying to figure out how we can deliver these sorts of collections of mechatronic systems in a way that built around courseware, built around flexible programming environments and application environments will give students those core skills. And yeah, it's something we're absolutely focused on for next year, and hopefully we'll start to be able to share sooner rather than later. But at the moment, it's all still some ideas and some sketches.
Great. How do you view a remote or online mechatronics course? What components do you think it should have? Again, given that it's quite a hands-on sort of area.
Yeah, absolutely. Completely remote. I think you always do need that hardware element. It's something you can't really escape when it comes to mechatronics, especially. As much as we do believe in the digital twinning and virtualization of these systems, as a hardware company, a company that's been building physical systems for over 30 years, we really do obviously see the absolute need for students to eventually validate on real hardware and see what the real world is like. And because of that, I think a completely online course, as much as you can replicate that, as I just talked about, with experiences that students can see components and see how those components interact with different virtual environments and how they can be connected together. That combined with even other online tools like MATLAB Simulink Online, or even some other electrical design online simulation systems and things like that, all of the new ecosystems that have been built on Spice and things like that, all of those together can give a lot of experience, but eventually having students see how that works physically is something I think, as much as possible, obviously in the last couple of years that hasn't even necessarily been possible, but as much as possible should be something the students do, even if it's just using a Raspberry Pi at home to run the code that talks to the virtual environment, which we've done, or add some additional physical sensors to that Raspberry Pi that then share their information with the virtual system or things like that. Like that kind of hybrid connection between the physical and virtual spaces is almost enough for them to see that when you take those theories and apply them to the real world, they sometimes don't work exactly the way you'd expect. Because that's ultimately the real outcome, both for control systems and for mechatronics, is that simulations are fantastic. They're a great way to learn the essentials and understand how these systems work, but reality is never exactly the same.
Um, so the example that you showed with the virtual QBot, you were using MATLAB Simulink, which is a fantastic platform. What other programming languages, or what do you think is the best language best suited for teaching mechatronics, if there is any single best?
Hmm, that's a loaded question. So if I to speak absolutely independent of my job to a certain extent, but really as a mechatronics engineer, if I were delivering a course in mechatronics, it's hard to say. I think, to be honest, I would probably aim for a hybrid approach. I would aim for something where, and this is something that we're trying to do as well, elements of a system that have very specific requirements in terms of performance, in terms of the sampling rates or the computational load that they need, have the language and the platform that is appropriate. So for instance, looking at something like Python, Python is increasingly everywhere. It's the ubiquitous language now. I think it is actually now the most popular language on the planet. Python is fantastic for a lot of things, and I would absolutely want a mechatronics course to be built around Python because it's an essential skill. It's something that really gives students an understanding of what programming is like without diving into the weeds that we used to have to do with C or assembly or even Java. But then if you're looking at Python as a real-time or high-performance language, unless that's backed up with hardware support like a GPU or something that has the horsepower to be able to execute those algorithms effectively, because it's not a compiled language, you just don't get that. So when you need something like high-speed control or sensor um, fusion or things like that, I would still introduce students to the concept of falling back on Simulink or falling back on C++, where that performance is there, where you can see the downside to a language that is, at the end of the day, a scripting language. So I would probably try to do both. But I think absolutely Python is a huge component of everything that you need to deliver to students nowadays, just because it is the most popular language in the world.
Absolutely. Last question, Pete. Thanks, audience members. Saying thank you for sharing your thoughts, which are perfect, which perfectly make sense for a university student. Just wonder how you would interpret mechatronics for college level students, which are more practical and emphasize on hands-on, that involve PLCs and other type
Yeah,
of equipment. What would be the best approach there to teach mechatronics?
absolutely. I mean, again, college is hyper focused on skills, hyper focused on industrial experience because of the destination of those students. And when students are going through a mechatronics program at that level, it has to be, again, that intuition and those skills that are going to serve them best when they deliver on those experiences in the real world, to building that portfolio for hiring committees and things like that. So I think there is still an element of the same experiences I talked about, things like using Python and even to a certain extent MATLAB Simulink as a platform for system level understanding are very useful. But I think you do absolutely need to introduce the platforms and skills and experiences that are key to those areas that you described, things like PLCs and ladder logic, things like how you integrate industrial systems with industrial power requirements, and a lot of the things that aren't necessarily as prevalent when you do more academic style design and integration, things like three-phase power or all of the industrial applications, HMI design. There's a whole lot of other things that come into industrial applications that are need to be introduced. And then obviously you can maybe take a step back on some of the more university or graduate level topics that are essential to those students. So maybe AI, machine learning, complex algorithm design doesn't necessarily have to be as key. You can focus more on the basics of control, the basics of state machines, and more fundamental building blocks of industry, but then maybe get a little bit more diversity in terms of the application areas and the platforms that are useful.
Well, awesome. Thank you. This brings us to the end of our webinar. A big thank you to everyone who joined us live today, and thanks, Pete, for this great presentation. For additional information on how our products and services can enhance your engineering labs in person or remotely, please visit our website at www.quanser.com or send us an email at info@quanser.com. And if you are on social media, specifically LinkedIn, don't forget to follow us there. Have a wonderful day and stay safe, everyone.
Thanks very much, everyone.